Hello, hello. Am I audible?
Yes.
Yes, ma'am.
Hello. Hello.
Yes,
Am
ma'am.
I audible?
Yes, ma'am.
Hello. Hello.
Yes, ma'am.
Your voice is not coming to me.
Hello, ma'am.
So let us start with today's topic, and that is unit number 4, relations. Okay. So last time we have started with the chapter relations. In that we have seen what is the relation, what is the domain and range of relation, and what are the different properties those are satisfied by relations. Okay. So first we are going to see what is the relation. What is the definition for relations. So here first point is definition of relation. A binary relation R from set X to Y, written as X is in relation R with Y, or R in bracket X comma Y. Means what? This relation R is in between X and Y. Is a subset of Cartesian products X Cartesian product Y. Means what? In short, we can define a relation as set of order pairs. Okay. So if there are two different sets X and Y, then what are the Cartesian product of this X and Y? That will be relation from X to Y. Okay. So a binary relation R on single set A is a subset of Cartesian product X Cartesian product Y. Means what? If there are two different sets X and Y, then what are the Cartesian product of X and Y? That will be relation from X to Y. Okay. So
Ma'am, your voice is not audible.
Hello? Hello?
Yes, ma'am. Yes, ma'am.
Hello, am I audible to
Yes,
you?
ma'am.
Okay, some problem was there. Your voice was not coming to me. Okay, so here we have started with the definition of relations. So what is the relation? A relation R is defined as set of ordered pairs. Suppose there are two different sets x and y, and relation R is defined from set x to set y. So it means it is a subset of Cartesian products x Cartesian product y. Is whatever order pairs will be there in Cartesian products of x and y, those order pairs defines a relation R. Okay. So again, if there are two different sets A and B, A is having cardinality as M, B is having cardinality as N, then maximum cardinality of relation R from A to B is given as M into N. So now suppose your set A is having number of elements as 3, B is having number of elements as 2, then relation R will contain total 3 into 2, that is equals to 6 order pairs. Means what? The cardinality, that is maximum cardinality of that relation R is 6. So this is the formula for same. So you can take note of this. Just take down definition of relations and how we can find out the maximum cardinality of any relation, and that formula is m into n. Okay. Now next point is domain and range of relation. Okay. So if there are two different sets A and B and relation R have order pair x comma y, then the domain of relation R, D of R, D is for domain, domain of relation R is a set such that X, for every X comma Y belongs to R for some Y in B. Means what? What is the meaning of this statement? Domain always refers to first element of every order pair from that relation. So that's why if you consider order pair x comma y, here x is the first element. That's why we are going to add that first element in domain of relation R. So likewise, if we want to find out range of any relation, then that is denoted by R of R. Means what? Range of relation R is the set such that if y is element, then for every y, x comma y belongs to R for some x in A. Means what? Range always refers to second element of each and every order pair from that relation. Okay. So keep in mind that domain always refers to first element of every order pair and range always refers to second element of every order pair from that relation. Now here one example is given. Let A is equals to 1 to 9, that is set of 1 to 9, and B is equals to set of elements 1, 3, 7. Okay. Now case 1 is given. If relation R is equals to, then R is equals to order pair 1, 1 and order pair 3, 3. So here we have taken this relation as equals to, means what? First element of that order pair must be equals to second element. That's why order pair 1, 1 is here, 3, 3 is here. Now we have to find out what is the domain and range of this relation R. So what we have seen? Domain always refers to first element. Now check here, two order pairs are here. So first element from first order pair is 1 and from second order pair it is 3. That's why domain of this relation R is 1, 3. So likewise, now we have to find out what is the range of relation. So range always refers to second element from each and every order pair. So second element is 1 and from second order pair it is 3. That's why the range of relation R is 1, 3. So likewise we can find out domain and range for any relation. So first of all tell me, have you understood what is meaning of domain and range? Hello? Have you understood it? Okay. So now we will continue with the next point. So again, case number 2 is given. If relation R is less than, means what? We have to find out such order pairs from this set A and B such that first element is always less than second element. So those order pairs we can define as 1, 3 because 1 is less than 3, again 1, 7, 2, 3 and 2, 7. Okay. So in all these order pairs, first element is less than second element. So again we have to find out domain and range for this relation. So domain is first element, that is 1, again 1 is repeated, 2, again 2 is repeated. So domain of this relation R is 1, 2. Now what is the range? For range again we are going to check for second element of each and every order pair. So from first order pair it is 3, then second one it is 7, again 3, 7. So we are going to write range of this relation R is set 3, 7. Okay. Now the next case is given as if relation R is greater than, means what? the first element of every order pair must be greater than second element. Okay, so we have to find out such order pairs from these two sets. So if you consider first element as 1, so nothing is greater than 1, that's why we are going to skip it. So if you consider 2, then for this 2 we can write order pair as 2 comma 1. Okay, then 9 comma 1, 9 comma 3, 9 comma 7. So from all these order pairs the first element is always greater than second element. Okay, so again domain of this relation R is first element from each and every order pair, and that is 2 and 9. 9 is common between all these three pairs, so we are going to write it once. And range is 1 3 7 because it always refers to second element. So this is the concept of domain and range of relation. Okay, now the next point is very important, that is properties of binary relations. So definitely you will get question of 4 to 8 marks from this point as properties of binary relations. So we have earlier discussed this point as there are total 5 properties of binary relations. First property is reflexive, second one is symmetric, third one is transitive, then antisymmetric, and last one is irreflexive. Okay, now we have to see what is meaning of all these properties. So first property is a reflexive property. So what is the definition for this reflexive? A binary relation R in set X is reflexive if for every x belongs to capital X, X is in relation R with X. Means what? The order pair x comma x must belong to relation R, or R is reflexive in X, that is set X. This is equivalent to for every x belongs to capital X, then x R x. Means what? That order pair x comma x must belong to relation R. So what is meaning of this reflexive property? For every x, means what? For every element of that set X, there should be order pair x comma x, and that order pair must belong to relation R. Then only we can say that that relation is a reflexive relation. Now consider example. Suppose your set X, that is capital X, is consist of two elements as 1 comma 2. Then when we can say that this relation is a reflexive relation? If order pair 1 comma 1 and 2 comma 2 belongs to relation R, then only we can say that this relation is reflexive relation. If there is only one order pair present, that is 1 comma 1 in relation R, then that is not reflexive relation. Why? Because here we have written if for every small x belongs to capital X. Means what? For every element of that x, there should be order pair x comma x, and that must belong to relation R. Then only that relation is called as reflexive relation. So take note of this property. Write down the property for this reflexive. This definition is very important. When they will ask you question like explain the properties of binary relations, at that time you have to give definition and one example for each and every property. Then only you will get full marks. Okay. Now second one is a symmetric property. So a relation R in set X is symmetric if for every X and Y in capital X, whenever X is in relation R with Y, then Y is in relation R with X. Means what? If there is any order pair 1 comma 2 present in relation R, then there must be any another order pair 2 comma 1, and that should belong to relation R. Then only we can say that that relation R is a symmetric relation. Okay. So that is meaning of this. X is in relation R with Y, then Y is in relation R with X. So we can say that reverse of each and every order pair must be there. Then only we can say that that relation is a symmetric relation. And for this you can take example as, if your relation R is containing order pair 1 comma 2, then it must contain order pair 2 comma 1. So relation 1 comma 2, 2 comma 1, this is a symmetric relation. Okay. So take down definition for this symmetric property. Okay. Now next point is transitive property. A relation R in set X is transitive if for every X, Y and Z in capital X, whenever X is in relation R with Y and Y is in relation R with Z, then X is in relation R with Z. So this is a transitive property. If there is any set X, and if X, Y, Z, these are the elements of that set X, then if X is in relation R with Y and Y is in relation R with Z, then X is in relation R with Z. Okay. So again for this you can give example as, if your relation is containing order pair as 1 comma 2 and 2 comma 3, then your relation must contain order pair 1 comma 3, then only that relation is a transitive relation. Okay. So how we have taken this 1 comma 2, 2 comma 3. Okay. So 2 is common between these two order pairs, so we have to cancel it. So what is remaining? 1 comma 3. So we have to check whether that order pair is present in given relation. If yes, then we can say that that given relation is a transitive relation. Okay. So take note of this, write definition and one example for same. next property is a irreflexive property. A relation R in set X is called as irreflexive if for every X belongs to X, order pair X comma X should not belong to relation R. So this is exactly opposite to reflexive property. What we have seen for reflexive, for every X, order pair X comma X must belong to relation R. Then only we can say that that relation is a reflexive relation. But for this irreflexive, for every X belongs to capital X, order pair X comma X should not belong to R. So if your set X is containing elements as 1, 2, 3, then your relation must not contain any order pair like 1, 1, 2, 2 or 3, 3. Then only we can say that that relation is a irreflexive. Okay. And here one important note is given. Any relation which is not reflexive is not necessarily irreflexive and vice versa. Means what? जर एखादं रिलेशन रिफ्लेक्सिव्ह नसेल तर ते इनरिफ्लेक्सिव्ह आहे असं त्याचं मिनिंग नाही आहे. देर आर सम रिलेशन्स दोज आर नायदर रिफ्लेक्सिव्ह नॉर इनरिफ्लेक्सिव्ह. ओके, सो हियर वन एक्झाम्पल इज गिवन. Suppose your set is containing 3 elements as 1, 2, 3 and relation is defined as 1, 1, 1, 2, 3, 2, 2, 3 and 3, 3. Okay, now first of all check whether this relation is a relation. So what we see for reflexive relation, there must be order pair x comma x for every x in relation R. Now check for first element 1 is there. Now check whether your relation is containing order pair 1, 1 S, that is there. Now 2, 2, no, this order pair is not here. That's why we can say that this is not a reflexive relation. Okay. Now check whether this one is a irreflexive relation. No, because order pair 1, 1, 3, 3, these are present in this relation. So what is the definition for irreflexive? There should not be any order pair x, x belongs to R. Then that relation is irreflexive relation. And such elements are present. That's why this is neither reflexive nor irreflexive. Okay. So this is regarding irreflexive property. So take definition for this irreflexive and take this note, which is very important. Now the last property of a relation is antisymmetric. A relation R in set X is antisymmetric if for every x and y in capital X, whenever x is in relation R with y and y is in relation R with x, then x is equals to y. So what is meaning of this antisymmetric property? If your relation is containing order pairs like 1, 2 and 2, 1, then 1 is equals to 2. If such a cases are there, then only we can say that that relation is a antisymmetric relation. Now if you consider this example 1, 2 and 2, 1, here we can't say that 1 is equals to 2. That's why this is not a antisymmetric. But if you consider the example as order pair 1 comma 1, okay, so here order pair 1 comma 1 is there. If you take reverse of this order pair, again you will get order pair 1 comma 1 only. That's why here we can say that 1 is equals to 1. So this is a antisymmetric relation. So likewise we have to think for this antisymmetric property. So all these properties are for binary relations. So hello, have you understood all these properties? Hello. Have we understood all these properties? Because these properties are very important. Based on these only, we have to solve further examples. Examples based on these properties. So before that, give me presenting. Roll number 1, 2, 3,
Yes, ma'am.
Present, ma'am.
4. Okay, 4,
Yes, ma'am.
5, 6,
Present, ma'am.
7. Roll number 7, 8, 9,
Present, ma'am.
10,
Present, ma'am.
hello.
Yes, ma'am.
Roll number 12, 13,
Yes, ma'am.
14.
Present.
Okay,
Yes, ma'am.
yeah. Roll number 14, present.
Yes, ma'am.
15,
Present.
16,
Present, ma'am.
17. Okay,
Present, ma'am.
18.
Yes,
Ma'am,
ma'am.
11, 12 तुम्ही म्हणलंच नाही.
हा 11, 12 घेतली होती. ओके 13 कुठे पर्यंत झाले 13, 14, 14.
Yes,
रोल
ma'am.
नंबर 14, 15,
Present. Present, ma'am.
16, 17,
present, ma'am.
18, 19,
Present, ma'am.
20,
Present, ma'am.
21, 21, 22,
Present, ma'am.
23,
Present, ma'am.
24,
Present, ma'am.
25,
Yes, ma'am.
26,
Yes, ma'am.
27,
Present, ma'am.
28,
Present, ma'am.
29,
Yes, ma'am.
30,
Present, ma'am.
31,
Present, ma'am.
32,
Present, ma'am.
33,
Present, ma'am.
34,
Present, ma'am.
35,
Present, ma'am.
36, 36, 37,
Present.
38,
Present.
39, 40,
Present, ma'am.
41,
Present, ma'am.
42,
Yes, ma'am.
43, 44, 45, 46, 47, 48,
Yes, ma'am.
49,
Yes, ma'am. Yes.
50,
Yes, ma'am.
49 is present. Okay. 50 is also present.
Madam,
51
madam,
is
45 is present.
45 is present. Is marked as present. 51 present. 52,
Present.
53, 54,
Yes, ma'am.
55,
Yes, ma'am.
56,
Yes, ma'am.
57, 58,
Present, ma'am.
58,
58
59,
present.
60.
है ना मैम 59 का मार्क बन रहा है प्रेजेंट तक
Okay. 60, 61.
यस मैम
Yes, 60 is
61
present.
present.
Okay. 62,
Present मैम
63, 64, 65,
प्रेजेंट मैम
66,
प्रेजेंट मैम
67,
यस मैम
68, 69,
Present, ma'am.
70.
Present, ma'am.
Now check for today's absent numbers. Roll number 7, 8, 16, 21, 36, 39, 43.
Hello, ma'am.
Yes.
Roll number 7 present.
36, 39, 43, 44, 46, 47, 57, 58 and 64.
Ma'am, 8 is present.
Okay.
58 present.
58 is present. Okay. Is it fine now? So today we are going to stop here. On next lecture we are going to solve some examples based on properties of relations. Thank you.